Okay, so we're given a problem with a strain rosette shown, and there's 3 strain gauges on a piece of stainless steel, and they go ahead and they give us the reading for each of these strain gauges. So at strain gauge A, the strain is equal to 475 microinches per inch, micro because that's just 10 to the negative sixth. The strain at B is equal to 200 microinches per inch. And we have strain at C, which is equal to negative 250 microinches per inch. So we have one that's negative. That's just because your strain gauge is going to be in compression rather than tension. Strain gauges are very directional, so if you have, say, some like strain going up this way, strain gauge A is not really going to be picking that up unless you have your Poisson's ratio thing and there's some kind of like necking, in which case it might pick that up. But basically, it's not going to pick up this strain that's perpendicular to it. It's just going to pick up the strain that's on the axis, and it'll be in tension if it's pulling on it, and it'll be positive in that case, or it'll be in compression, in which case it's negative. So A is in tension because it's positive, B is in tension because it's positive, C is in compression. And just as a note with the units here, that's inches per inch. That just goes back to how strain is measured, right? It's just your change in length over the initial length, right? Both apparently are measured in inches here. So I guess that it's a hint that we're in the SI system. And the fact that the problem asks us to put things in KSI is a good indication of that as well. So from here, what we want to do is get these strains in terms of strain X, strain Y, and gamma XY, right? Because if you think, if you have your stress block, right, and it's on some coordinate system, we want to find the the strain at Y and the strain at X. And gamma is the angle of which it's kind of twisting at, right? So that's going to be gamma XY. And that's going to be helpful information for us so that we can find our principal stresses and our maximum shearing stress. So how do we do that? How do we get these strain gauges in terms of strain X, strain Y, and gamma XY? Well, we have some strain rosette equation, a strain rosette equation, that is going to be helpful here, where we have the strain at some point is equal to the strain at X cosine squared theta of that strain plus strain at Y sine squared theta at that strain plus gamma XY. And that's going to be sine theta cosine theta. And strain is just going to refer to your strain gauge reading, and theta is just going to refer to the angle at which your strain gauge is off of the x-axis. If it's going to be clockwise, that's going to be negative, and if it's counterclockwise, that'll be positive. So we have 3 unknowns here, right? We have strain at X, strain at Y, and gamma XY. But we also have 3 strain gauges, so we should be able to make 3 of these equations and solve for our 3 unknowns, and that should be enough information. So the cool part is that we kind of already have one of our unknowns solved for us because strain gauge A is already directly on the x-axis, so it's already measuring the axial strain right there. So we can go ahead and say that the strain at A is going to be equal to the strain at X, and that's going to be equal to 475 microinches per inch. And for the other 2, we're not going to be so lucky. We do have to use this big equation, so we'll go ahead and we'll do that for each of them. So strain at B, which is equal to 200 microinches per inch, is going to be equal to strain at X, which we just said, right, was 475 microinches per inch, multiplied times cosine squared, and theta, right, where it's just the angle off the x-axis again, and it's clockwise, so that's going to be negative 60 degrees, plus strain at Y, which we don't know, sine squared, negative 60, plus gamma xy sine negative 60 cosine negative 60. Okay, so the first thing we can do is we can evaluate this first term up here because that's just going to be a constant. So we'll go ahead and we'll say 60 negative cosine, that's going to be 0.5, squared is 0.25, times 475 is equal to 118.75. And we'll go ahead and we'll flip that up to the other side of the equation. So that's, we'll go ahead and we'll get 81.25. 81.25 on the left side of our equation. And then we're just going to go ahead and simplify the coefficients for each of these two terms. So we'll go and say 60 negative sine squared is just equal to 0.75. Strain at y. And then we'll go ahead and multiply 60 negative cosine times 60 negative sine. And that's going to be equal to negative 0.433 gamma xy. And so that's our first equation that we will be using to solve for strain y in gamma xy. And we'll make another one for our strain at C. So we'll say our strain at C is equal to negative 250 micro inches per inch, which is equal to, again, we already know strain x, so we'll say 475 micro inches per inch, multiplied by cosine squared. Now our theta has changed, right? Because we're at strain gauge C now. So strain gauge C is going to be 120 degrees clockwise off the x-axis, so that's going to be negative 120, plus strain at y, sine squared, 120, negative 120, plus gamma xy, sine negative 120, and I'm running out of room, but it's cosine negative 120. And that's multiplied into that term. Okay. And we just simplify again. So we have 120 negative cosine squared is equal to 0.25 times 475. Oops, I have to do that again. 475 times 0.25 is equal to 118.75. And we'll go ahead and we'll flip that onto the other side of the equation. And that's going to be negative 368.75 micro inches per inch. And that's going to be equal to the strain at y. Sorry, I'm getting ahead of myself. Let me go ahead and simplify this term, negative 120 sine squared. Sine squared. So that's going to be 0.75 strain y. And we'll go ahead and simplify this term by multiplying 120 negative cosine times 120 negative sine. And that's going to go ahead and be equal to plus 0.433 gamma xy. Alright, and that's our second equation. Cool. Okay, so now we just have to substitute and solve. So I'm going to go ahead and take this second equation and solve for strain y. I'm going to go ahead and put negative 368.75. And I'm going to go ahead and not write out the units, but everything is in micro. Minus 0.433 gamma xy is equal to 0.75 strain y. And then, of course, we will go ahead and take 368.75 divided by 0.75, and that's going to be equal to negative 491.666 minus, we'll go ahead, 0.433 divided by 0.75 is equal to 0.57733 gamma xy. And that's equal to our strain at y. So we'll go ahead and we'll plug that in to our first equation up here. We'll say, yeah, 181.25 is equal to 0.75. And we'll just plug in this whole term for strain at y. and we'll say negative 491.66 minus 0.5773 gamma xy, and then minus 0.433 gamma xy. Remember, this is just our first equation up here with this plugged in. Okay, I'm going to go ahead and distribute in our 0.75 right off the bat, and we can go ahead and say that 0.75 times 491.666666 is equal to 368.75 negative minus 0.5773333 times 0.75 is, of course, 0.433 gamma xy minus 0.433. Okay, so we'll go ahead and I'll put this term and swing it over to the left side of the equation and add these two up. So we have 81.25 plus 368.75 is going to be a nice even 450, and that's going to be equal to negative 0.866 gamma xy divided by 0.866. That's going to go ahead and give us a gamma xy equal to negative 519.63, and this is going to be microradians. Remember, because this is actually this is an angle. It's not a strain value. And now that we have solved for gamma xy, we'll go ahead and plug it in to our first equation once again. So I'm going to keep that up. 81.25 is equal to 0.75 strain y, which is what we're solving for, minus 0.433 negative 519.63. And we'll go ahead and solve for that. Times 0.433, that's 225, which I'll go ahead and put on to the other side, plus 81.25 is going to go ahead and give us 306.25 is equal to 0.75 strain y divided by 0.75. Algebra. Ooh, did I do that right? Sorry, I'm going to double check. So I have 519.63 times 0.433, 225. Oh, but that's positive. I see what I did wrong. So, my bad, guys. This is a positive term overall, so that's going to be overall minus to the other side, which is going to give us negative 143.75 is equal to 0.75 strain y divided by 0.75, and that's going to go ahead and give us a strain at y of equal to negative 191.66, etc. So that's pretty rad. Now we have everything in terms of what we need it to be in terms of. In strain x, strain y, and gamma xy. Where's my strain x? Here. All the way up here. And as you can see, we have a pretty large positive strain x, a smaller negative strain y, and we can kind of do a sanity check. We know that C is larger in magnitude and it's compressive as compared to B, which is smaller in magnitude and in tension. So it would make sense that we would have an overall compressive Y strain. As for A, it's in tension and it's right along the x-axis, so that makes sense. And we can expect that the tension and compression of strains C and B would kind of cancel each other out, which might lend itself to the reason why it's a bit smaller than strain A. So I'm going to go ahead and rewrite. I'm just going to go ahead and put strain X is equal to 475. This will be micro inches per inch. This is also a micro inches per inch. And from here, we need to take two steps. One is we need to convert strain into stress because we're looking for our principal stresses, not our principal strains. And we also need, into stress. And we also need to find our principal stresses. Now, you could also flip these steps around and find your principal strains and then convert those strains into stresses. But just the way I'm going to do it, I'm going to go ahead and convert our strains into stress first and then find the principal stresses off of that. And so the way I'm going to do that is I'm going to use generalized Hooke's law. Hooke's law. Which I'm just going to go ahead and write out, and then I'll kind of give some commentary on it, is equal to modulus of elasticity 1 over minus Poisson's ratio squared multiplied times strain x plus Poisson's ratio strain y, and then stress y is equal to modulus of elasticity 1 minus Poisson's ratio squared strain y plus Poisson's ratio strain x. So your modulus of elasticity, right, is just going to be equal to your stress over strain. So that's a good way to start by converting stress and strain. Modulus of elasticity is just going to be a constant that you find depending on the material that you have. It's also good to note that we're kind of assuming that stainless steel is deforming elastically here because we're using the modulus of elasticity, which is just the slope on your stress strain graph. And so we're assuming that the deformation is in this linear region here and it's not deforming plastically. Poisson's ratio is equal to negative strain x over strain y, or any two strains that are kind of perpendicular to each other, so it could be strain x over strain z or something like that. And that kind of has to do with this whole thing with necking. Oh, I'm sorry about this. This happened again. I'm going to have to go change my color to black. Okay, so this has to do with necking, right? It's because if you have some, material here and you stretch it out, it's going to get skinnier and longer. And that means that if the strain in one direction is in tension and it's getting longer, then the strain in the opposite perpendicular direction, it's the opposite sign. So it's getting smaller. Like the deformation is becoming shorter instead of longer. And that's what Poisson's ratio is about. And so you can manipulate these relationships mathematically and get generalized Hooke's law. And you can do that for 3 dimensions, but for 2 dimensions, this is what these equations look like. They would look different if you had them in 3 dimensions, but we're not working in 3 dimensions, so we just have these. And we do need to find some constants here. Modulus of elasticity and Poisson's ratio both are constants that are particular to your material. And the material we have, I believe, was like AISI stainless steel. And to find your modulus of elasticity for stainless steel, you can go ahead and I'm going to look up the textbook and go to Appendix B. You could also Google it, I guess, but I have the textbook, so might as well use it. And is this 302 stainless steel? Hold on, let me go up. Yeah, 302. Did I get AISI? Yeah, okay. So it's 302 stainless steel. And it says our modulus of elasticity is going to go ahead and be equal to 28 times 10 to the 6th psi. And the book also gives us a modulus of rigidity, which is 10.8 times 10 to the 6th psi. What the book doesn't give you is Poisson's ratio, but luckily there's a relation with Poisson's ratio given between your modulus of elasticity and your modulus of rigidity. It looks something like this. So G is equal to E over 2, 1 minus Poisson's ratio. And you can kind of rework this, and you would see, right, you have V is equal to 1 minus 2 G over E, and we can go ahead and plug numbers in. Since we are given E and G, we'll say 2, G is 10.8 E to the 6th divided by 28 E to the 6th. And we'll go ahead and plug that in. So 10.8 E to the 6th times 2 divided by 28 E to the 6th, and then minus plus 1. And you would end up with a number for Poisson's ratio that's going to be equal to 0.228. And that is going to be unitless. That's a ratio because it's psi over psi. Okay, so now that we have our constants that are important for generalized Hooke's law, all we have to do is kind of plug numbers in. So I'm going to go ahead and do that. So we'll find stress at x is going to be equal to Poisson's ratio, which is 28 E to the 6th, divided by 1 minus 0.228 squared, times strain at x. We'll go up. What do we find? Strain at x is 475 microinches per inch. We'll say 475 micro inches per inch plus Poisson's, which is 0.228 times our strain at y, sorry, which is negative 191.66. And we can go ahead and solve for that. Your stress at x is going to be equal to 28 E6. Well, actually, I'll start at the bottom. 0.228 squared. So you get something like 28 E6 divided by 0.948. And that's 475 micro inches per inch plus, and we'll go ahead and say 0.228 times 191.66 blah blah is equal to, and it'll be negative, sorry, it'll be negative 43.6. We'll say 43.7. We'll round that up. Now, we'll go ahead and reduce this more. We say 28 E to the 6th divided by 0.948 is going to give us a super big number, which is 1, 2, 3, 4, 5, 6, 7. That's like 2.953 E to the 7 multiplied by 475 micro inches per inch. Or actually, you know what? Sorry, I can go ahead and minus, we'll say 475 minus 43.7 is going to be equal to 431.3, and that is in micro inches per inch. And from there, I can multiply that times 2.953 E to the 7th, and that's going to give us a pretty big stress, actually. It's going to be equal to 1.2736 E to the 10th. Is that right? That seems kind of big. I'm going to double check my math. No, that should be that big. That's 191.66 EE6 negative times 0.228. Right. Okay. Minus plus 475 EE6 negative is equal to that times 2.95 EE to the 7th. Okay, so yeah, that is kind of big. I just misplaced a 0 on my calculator, so sorry about that. It's the real number is equal to 127 to 3.39. And that's going to be in PSI. And to make this a little neater of a number, we'll go ahead and put this in 12.7 KSI. Okay, cool. And then we'll solve for stress at y. And we already know this is going to be the exact same thing, right? Modulus elasticity over 1 minus Poisson's ratio squared. It's going to be this number, so I'm just going to go ahead and bring that down. 0.953 e to the 7th. And multiplied by now this whole term, which is going to be strain at y, which is negative 191.66, plus Poisson's ratio, 228, times strain at x, which is 475 points. That's going to be micro inches per inch. This is also micro inches per inch. Sorry about that. I keep sometimes not doing that, but generally it's in micro something. Okay. So strain y is equal to 2.953 e to the 7th. And I'm going to go ahead and I'm going to say 475 e to the 6 negative times 0.228 is equal to that. And that's going to be that minus 191.66 e to 6 negative. And that's going to give us a negative number, negative 8.3 EE 2, 3, 4, 5 e to the negative 5. Something along those lines. And we'll multiply that times 2.953 EE to the 7th. And that's going to give us a number negative 2461.62 PSI. But to make this a little bit more better looking, we'll say negative 2.46 KSI. And now all that's left is to find tau xy. So tau xy is also has a relation, but it's much easier than the stress relations. It's just g times gamma xy, which is going to be equal to, what's g? G is 10.8 times 10 to the 6th. 10 10.8 times 10 to the 6th. G, what's gamma xy? But our lovely negative 519.63 microradians. Value. And that's going to be equal to, we'll go ahead and plug that into the calculator. X3, 519.63, E6 negative is equal to that, times 10.8 e to the sixth is going to be equal to negative 5.612, and that's going to be in PSI. And of course, we'll change that to 5.61 KSI. Okay, so long hard journey, but now we have our strain data. First we put it in terms of x and y, and now we're going to put it in terms of stress. And now all we have to do is find the principal stresses off of these stresses. So I'm going to go ahead and actually rewrite strain x here. Stress x. Stress x here, 7.2 KSI. And kind of scroll down a little bit. And to find our principal stresses, what we can do is use Moore's circle. Moore's circle is a really good way of kind of finding your max and min stresses by essentially shoving your relations between the x and y stresses on your like stress block into the equation of a circle. And it's a nice geometric solution, so you can kind of avoid doing too much math. So the first thing you want to do, I guess, well, before we start getting to Moore's circle, we can go ahead and kind of make like a mock little stress block here, right? And just so you know, since our stress at y here is going to be negative, it's going to be compressive in this direction. And since our stress at x is going to be positive, that's going to be in tension. And since our tau xy is negative, then it's going to be this way. And that makes sense, right? Because if your positive y is that way and your positive x is this way, then you're going to have a negative y value, but a positive x value multiplied together is going to give you a negative tau xy. This is stress at x and this is stress at y. Okay, and we'll go ahead and we'll make the cool thing about using this program, I can kind of cheat. I'll use a line to make our little coordinate plane. And then the first thing we're going to do is decide which way our axes are going. I'm going to go ahead and put positive stresses over here and positive shear stresses this way. Have I been calling this strain? No, I don't think so. Have I? Okay, if I called this strain, this is not strain, this is shear stress. I had a mental fart there if I did. Okay. So our positive shear stress is going to be at the bottom and our negative shear stress at the top. I do this because I saw it on a YouTube video, and it makes it a little easier when you try to find the angles for the principal stresses and such. Also, you can just kind of start and put the stress x value along with your immediate shear stress value. Anyways, I just find it to be a bit more intuitive. So the first thing we're going to do is we're going to plot stress x, which on the stress line that's going to be equal to 12.72. We'll say that's somewhere around, I don't know, here. We'll say that's 12.72. And that we'll plot that against our tau value that we already have. And tau is going to be negative, and negative is going to be up. So we'll say that's negative 5.61. And so we have a dot right there. And same thing, but opposite for our stress y. Stress y is going to be like a negative 2 value, so that's going to be negative 2.46. And we have like a dot right there. And to find the center of our circle, center is just going to be equal to the stress average at 0. And stress average is just equal to our stress x plus stress y divided by 2, which is also equal to 12.72 minus 2.46 divided by 2, which is equal to, I'll plug that into the calculator, 12.72 divided by, 12.72 minus 2.46 divided by 2. That's going to give us stress average of 513.313. And we'll say that's our center. That's 513. 5.313. Okay. And I don't know if I can cheat again with my tool here. I could do ellipse maybe. Oh, I don't know. Whoops. That's not great. Let's see if I can do it this way. I'll do like, no. Okay, this is harder than I wanted it to be. I'll just do it freehand. It'll be gross, but this will be what it'll be. And that's our circle. Sort of. Pretend it looks nice. Yeah. I don't know why it's erasing. That's interesting. I'm going to go ahead and check out my window. Okay. Okay. So, now I'm going to go down here. It's going to be like that kind of a circle. All right. So, our principal plane is generally along the x-axis. Why? Because if we're trying to find our principal stresses, as in our maximum and minimum stresses, what is the furthest point on the circle that will give you a maximum or minimum stress? And that's going to be on the x-axis, right? I mean, because if it's up here, then you have some smaller stress value, but if it's all the way over here, then that's going to be your max stress value. Same for the opposite direction. So to find our max stress values, a good thing to know would be the radius of the circle. And we can find this relatively easily just using Pythag. So I'm going to go ahead and do that. Is going to be equal to rad. Now, that's going to go ahead and be 12.72. 12.72 minus 5.13 is equal to roughly 7.6 squared plus, and that's going to be a negative 5.61 squared, and we'll rad that out, and it's going to be roughly, your radius is roughly going to be 9.438. And what we can do with this is super rad. That's our tau max, right? That's going to be our shearing stress maximum. Why? Because if we're looking for our shearing stress, which of course is on our y-axis, and we're looking at the point that's highest on the circle, it's just going to be straight up. And that distance is just our radius. So that's going to go ahead, and I'm going to go ahead and put this over here. I'll say tau xy, tau max is going to be equal to 9.438. And remember, we did everything KSI all the way up here, so this is also going to be KSI. And if we want to find our principal stresses, all we have to do is we say stress 1 is going to be equal to the stress average plus R, and stress 2 is going to be equal to stress average minus R. And that makes sense too, because we're starting at the center of the circle, right? That's stress average. Plus R is going to be the furthest point towards our stress signal, and minus R is going to be furthest point just on the opposite side. And so that's going to go ahead, and that's going to be equal to 5.13 plus 9.438, or 5.13 minus 9.438. And that's going to be equal to plus 5. On one side, 14.568 KSI. And on the other side, negative 4.308 KSI. And I believe that is the whole problem. It asks for your principal stresses and your max shear stress, and those are your values for that. And again, kind of a sanity check. You have your stress, principal stress 1, 14 KSI is a pretty reasonable value to get, especially since this is stainless steel. So it's gonna need a lot of stress for it to be deforming at all. Yeah, that's the end of the problem. Thanks for listening.